Okay, class. We're going to talk about solving systems of linear differential equations by the elimination method. So we talked about systems of D.E.s a little bit. We had a part of section 1.2 or 1.1 where we took a solution to a system and you guys had to plug it into that system in order to verify that it was a solution. That's one thing that we did. The second thing that we did was in chapter 3, 3.3 I believe, where we created a system of differential equations, but we have not talked about solving them at all. This is the first time we're going to solve it. Okay, so we're going to use a combination of some of the methods that we have gone over already. There is quite a bit of the annihilator method in this section. So if you want to, I would suggest, if you're fuzzy on that, I would suggest that you go back and you revisit that video real quick, or at least look at the script write-up or the solutions that we posted. But we are going to go over the undetermined coefficients annihilator approach to solving these things. Okay, so that differential operator notation will appear here, so just make sure you're familiar with that before we get started. Okay. So, first let's go over the steps for what it is that we're going to do. It's basically a 6 to 8 step process, depending on how you want to look at it. Maybe more than that, but it's pretty straightforward. So the first thing we want to do is we want to take all of our dependent variables, basically all of the functions that we have. So far we're used to having just one function, y, as a function of x. Here we're going to have multiple because we have a system, right? So there's more than one function that we're going to have in our equation. It could be x, y, and z functions as functions of t, or it can be y1, y2, y3. You know, we've seen that quite a bit as well. But we're going to have basically two dependent variables. Those dependent variables, again, they are functions of our independent variable. Right? So we want to get all of those things on one side. Our independent variable, in this case t, it doesn't really matter where we put it, but generally we kind of want to have it all on one side. But if we can't isolate it to one side or the other, it doesn't matter. Okay, but we do need to have all of our independent our dependent variables, our functions, all need to be on one side of the equation. Right? So what we're going to do is we're going to rewrite these functions that we have, those dependent variables, in their differential operator notation. So again, we're not annihilating them, we're just rewriting them. Okay, so we will annihilate things using the annihilator method, but not yet. We're just going to substitute in those differential forms, right? So if I have y to the nth order, I'm going to substitute it with dny. So a lot of times we write it as subscript y. Here we're going to multiply it as dn times this y function, because that's what we're going to be using here, right? Here, if I have x to the nth, this is not nth power. I guess I forgot to fix that real quick. But the nth derivative of our function x, I will rewrite it as this form of an operator. Okay. So we're going to use the elimination method that we know from our standard regular Algebra 1, Algebra 2 courses, Algebra 1 actually, where we want to eliminate a variable, right? So what we're going to do is we're going to choose either all of my y's or all of my x's, and we're going to eliminate that, right? And the way that we eliminate it is by multiplying one or two of the equations by whatever it is that we need in order to get them to be identical, so that I can add my two equations or three equations together and get those terms to eliminate, right, to disappear. Okay. After that, I'm going to have a resultant equation, right? I'm going to add two equations together. It's going to eliminate one of these variables, so I will have one variable left in an equation. So then what I want to do is I want to use the annihilator method on that resultant differential equation that I get. I'm just going to use the annihilator method, right? So again, the stuff that we have from I believe it's chapter 4.5, maybe it was 4.6, I don't remember. Okay, so what we're going to do then is I'm going to repeat the steps 3 and 4, but for the other variable. Okay, so if I eliminated y first and got out x's, I will go back and I will eliminate my x's and then use the annihilator method on y. If I had a third variable, z, I would do that again for z, right? So I'm really just going to repeat these steps a few times, okay? After that, I will have general forms of solutions made from this annihilator method. So I'm going to have a whole bunch of coefficients. So I want to make a system of equations basically through the rest of the annihilator method of undetermined coefficients by taking the derivatives of the particular solution and the derivatives of the general solution and then subbing them back into my system and solving for my coefficients. The first set I'm going to solve for, though, is the particular solution. I'm going to find those values first if it was a non-homogeneous system. Okay, if it was a homogeneous system, I don't even have to care about I because there is no particular solution, right? But if there is, I need to go for those coefficients first, and then I can solve for the coefficients of the general homogeneous system. So let's do an example. Okay, here's our example. I want to solve dx dt minus 4y is 1 and dy dt plus x equals 2. So if you notice, I have two variables, x and y, right? X is a function of t, y is a function of t. Again, I told you I kind of hate this notation, so I am going to go ahead and change it into the prime notation. Okay, so especially when we start doing higher order systems and systems of equations and higher order equations, we really don't like the dx dt's too much. You can keep using them if you want, but they're important in the linear first order equations because we do separation of variables and things like that. We don't do that for the higher orders or for the system, so I like to just keep the prime notation, right? So what I want to do, again, if we go back, my first step, okay, is move everything to one side. It's already to one side. So the next thing I want to do is I want to rewrite my dependent variables into this operator, the differential operator notation. Okay, so x prime is dx, y prime is dy. Now what I want to do is I want to annihilate one of these. Either I want to get rid of these y's or I want to get rid of these x's. I actually chose to eliminate x's first. So this is dx. Down here I have just an x. So what do I need to eliminate it? I need it to look like dx. So how do I do that? I multiply by the differential operator d. So then this will be d squared y. This will be dx. And remember, this is the differential operator. It is not 2D. It's a constant. It is acting on this thing. It's differentiating this. It's differentiating this twice. And it's going to differentiate this. So this is going to go to 0. Okay. So now what I can do, because I have a positive dx and a positive dx, is if I subtract these things, the dx's will cancel. So I got a negative d squared y, a negative 4y, right, minus a minus of nothing, so it's minus 4y, and 1 minus 0. So this is my resulting differential equation. If you look at this, it is really y double prime minus 4y equals 1. That's what this equation is. If you want to go ahead and just solve it from here, that's fine, but we're already in the differential operator method notation, so we're going to continue on with that process and solve it as a annihilator method. Okay, so what I'm going to do is I need to solve this thing. Okay, I need to finish this. This is my resultant equation. This is now not a system but a single equation that I can solve because it's a single dE. Okay, so notice that I can, ideally I would not have a negative in front, so I can multiply everything by -1. Okay, I can actually factor out this y, right? So now this is the equation that I want to solve because it'll give me the solutions for what is on this side, which is the homogeneous side. but I have the non-homogeneous portion over here. So what I can do is I can annihilate this, right? So again, we are revisiting the annihilator method. So I can multiply everything by d because this d annihilates the constant. So now it's equal to 0. The solution to this d is the solution to my particular system, and the solution to this part is the solution to my complementary homogeneous solution, right? So I got these two zeros, right? This gives me an imaginary answer, and this 0 goes with the non-homogeneous portion, right? Note that m equals 0 is for the non-homogeneous solution, right? Because that's what annihilated the -1. So then my solution looks like this. The 2i gives me this form for my general solution, and my y of p is this constant, right? So constant 1, constant 2, this gives me a constant because it comes from the non-homogeneous portion. Okay, so now what I'm going to do is I'm going to go all the way back, okay, all the way back to about here. I can actually jump to here because I went into the differential operator notation, and I'm going to solve not by eliminating x, but instead by eliminating the y's. Okay, so let's eliminate dy. So if I want to eliminate dy, notice that this is a 4y and this is a dy. This is missing a d, this is missing a 4. So I multiply this by the differential operator d. I multiply this by 4. So this will be d squared x minus 4dy, and this operates on this constant, so it turns it into 0. Okay, so all of this is times 4, and this has been operated on by the differential operator. Now they have different signs. One is minus, one is plus. So if I add them together, the y's will cancel, and my equation will be left with nothing but x's. Okay, so again, this is my resultant DE. This is the one I need to solve. If you want to pull it out and solve it using another method, then that's fine. But again, I'm already in the annihilator method, so I'm just going to finish up using the annihilator method because all I have to do is factor, right? If I do it any other way, then I have to, I don't know, variation of parameters. I'd have to divide by, well, I guess it's already in the regular notation. I mean, there's other things I can do, but I'm already in this annihilator form, right? So let's solve this. So I want to solve this portion. Notice I can factor out the x's. Okay, I have the same base here for the homogeneous portion. That is not by accident. You should you should always get the same solution for the homogeneous portions of your variables, x, y, z's, y1, y2, whatever. They should always be the same. And we'll see why later in a couple of chapters from now. Again, notice I have the non-homogeneous part, so I would like to annihilate that so I can multiply everything by the differential operator d. Okay, so again, the solution here is for the non-homogeneous part for the particular solution, and this solution here goes to the homogeneous portion. So I got the same zeros, and then this is my general form of x. All right, now I need to solve for my coefficients, C1, C2, C3, C4, C5, C6. Remember, I want C4 and C5. I would like those to be in terms of C1 and C2. Okay, I don't want a whole bunch of different coefficients, especially since the bases here are the same. I want them in terms of the same coefficients. Okay, C3 and C6 I should be able to solve exactly for, because they are particular solutions. Right, so I want everything in terms of C1 and C2 because those are the variables that are on the y function. And it's not because they're on the y function, it's just because the general solution for x and the general solution for y are identical, right? So since C1 and C2 were the first coefficients I had, I want these to have those coefficients also. Okay, so I'm not going to just substitute them, but C4 is some combination of C1 and C2. Same with C5, it's some combination of C1 and C2, right? So these particular solutions should also be found. These ones can be found exactly. C4 and C5 will be written in terms of C1 and C2. So C4 will be like 5C1, and C5 will be like negative 2/3 C2. But XP and YP, those are going to be actual values. 28, negative 74. I need to actually solve for these values. Okay. So that's the ones we solve for. We start with the particulars because once I use my particulars, they are going to affect my solutions for C4 and C5. So I do these things first because I can find them exactly, right? So if I take XP as C6, its derivative is 0. Same thing if I take my YP, right? Its derivative is 0. So when I take those things, let's go back real quick, and I plug them into my DE, I'm going to plug it into this form, okay? Not X prime, but XP prime. Not 4Y, but 4YP. YP prime, XP. Because those are the things that I have now. Those are the equations that I'm using, right? So when I plug them in, but I'm not plugging in, I'm really just doing substitution, right? Let's try what I'm trying to get at. So when I plug the actual values in, remember the prime functions are 0, right? And XP and YP are coefficients, right? Unknown coefficients. So this is going to be negative 4 C3 equals 1, right? And this is going to be 0 minus C6 equals 2, right? And then that makes it very, very easy to solve for. C3 is just negative 1/4. C6 is negative 2. Okay, so now I have those particular solutions solved for. I need to go ahead and try to solve for my C4s and C5s now, right? So X of G has this form, Y of G has this form, so notice they're identical, but they will have different coefficients. And remember, that comes from when we're going over the annihilator method. Okay, so again, if you need a refresher, go back and visit that video or the write-up that I have for you guys so you can brush up. Okay, so my derivative of xg, maybe I should wrote xg prime, that's fine. The derivative of this is this thing. Okay, the 2 comes out, cosine changes to a negative, so it turns to negative C4, cosine turns to sine, right? Same for sine, and my yg, its derivative looks like this also. Okay, so again, this is yg prime, this is xg prime. I just got lazy, I guess, and I didn't write the subscripts, but you know that these are the equations we're solving for right now. So if I plug these things back into my system, right, just like I did for the particular solutions, I will get this long thing out, right? So this is x prime of g minus 4 times y of g, right? These are all positive, so now they're negatives times 4. And then same thing here, I take my y prime of g and I subtract my x of g. And those are going to be equal to 0. They're not equal to those 1 and 2s or whatever values I had, because this is for the general solution. This is for the homogeneous case. I already solved for the particular solutions. Okay, I don't need to throw in the 1 and the 2 here anymore. I already have those values solved for it, right? So I'm setting it equal to 0 because it's now the homogeneous case. So now what I need to do is just kind of notice what happens here. Okay, I got a bunch of sines and cosines. I really would like to add this cosine with this cosine, but notice that these things, this cosine 2t can only be 0 if it cancels each other out. Okay, and these two sines have to cancel each other out in order for it to be 0. Same thing with the second equation. So we'll call this equation 1, we'll call this equation 2, right? So in order for this and these two to combine and be 0, these have to cancel each other, these have to cancel each other, these have to cancel each other, and those have to cancel each other. Okay. We also want to look at, can I go top and bottom with anything? And I can't, because if I look at my cosines, I got 1, 2, 4, and 5. None of those have similar coefficients, so I can't add these together to get things to cancel. I can if I start multiplying stuff, but I really don't want to go that route. I can, you know, don't get me wrong, but I'm not going to. Okay, I'm just going to use the equalities in each equation. Right, so from equation 1, C5 minus 2C1. You might be like, well, what are you talking about? This 4 and a 2. Well, notice 2, 2, 4, 4. They're all multiples of 2 on the top function, not on the second one, but on the top they are. So if I divide everything by 2, -1, +1, -2, -2, right? So for cosines, this is just a C5. This is just a -2C1 because I'm reducing all of them by a factor of 2, right? So if I add those two pieces together, they got to go to 0. If I do the same thing with sine, -C4, this is twice as much as that one, so -2C2, that's going to be 0, right? So that's my system I have from the first equation. For my second equation, I have another system, okay, that I form the same way. But I want you to notice between the two systems, between equation 1 system and the equation 2 system, it's all one system to me, right? But notice that the first part from equation 1 is identical to the first part from equation 2, and the second part of equation 1 is the same as the second part from equation 2, but opposite signs. Minus minus, plus plus, right? C2 and C2, C4 and C4. It's the same thing. Positive C5, positive C5, -2, -2. It's the same deal. So I really only have to solve one of these systems. Okay? And remember, I'm trying to find C5 in terms of one of these equations. So the easiest thing to do here is just to take C5 and move this to the other side, so I know C5 is equal to some form of C1. Same thing for C4. Okay, the easier one to use is this one though, because then I can just take this and subtract it over. So that gives me my two solutions. C5 is 2C1, right, from here. C4 is -2C2. It was easier to use this one to get to that place. So these are my coefficients for C4 and C5. Now everything is going to be in terms of C1 and C2. Okay, so these are my equations. This is the non-homogeneous portions, and then now everything is in terms of C1 and C2. That is my final answer.